So how do you get good at chemistry, right? So the thing about chemistry that's interesting is that, of course, it's just like any other class where you have to study. Oops. It's just like any other class where you have to study, right? But the more important thing in chemistry is actually practicing problems, so that when you get so that when you encounter a problem, you're able to read the question and parse out the information to find what's important and use that to do math, right? Because you'll find that in every chemistry problem there's a chemistry part and there's a math part, right? And you can't get through the problem without doing the math part, okay? The chemistry part is the part where you use to find out the information that's important, and the math part is self-explanatory. You do the math to solve the problem, right? So, and then you get the answer, and that turns back into the chemistry part. So, let's talk about some very simple mathematics stuff just to make sure everybody's on the same page, right? And just so that I know that I covered everything, right, that I wanted to cover in this little math primer with you guys. I have some notes here. So the first thing is, let's talk about decimal places. Decimal places, right? That's going to be super important for the next few chapters, right? So say I have a number 2,518.407 grams. And so the places are, the decimal places are actually named, of course, right? We have here is the ones place. This is the tens place. This is the hundredths place. And this is the thousandths place, okay? And then if you go to the right of the decimal point, you have the tenths place with a th, right? Tenths place. Then you have the hundredths place with the th, right? And then here you have the thousandths place with the th, okay? Thousandths place, okay? So that's important to know because you're going to have to be able to do this thing later called significant figures and know where these decimals are, okay? So that takes us to learning about or reviewing positive and negative numbers. So if you have a number line and the center is 0 and you go to the right of it, 1, 2, 3, 4, 5, 6, these are all positive numbers. Okay? And then if you go to the left, 1, 2, 3, 4, 5, 6, these are all negative numbers. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. And I need to blow my nose again, so I'm going to stop this and sorry, I'm super stuffy today. It's probably because the weather keeps on going back and forth between uh, below freezing to above 70. So making my nose all runny. Kind of bad there. Somebody last week said that they came from bipolar weather. I think this is what they were talking about. Whoever that was, let me know. All right. So we have our numbers, right? So when we're doing arithmetic with those numbers, right? I like to, instead of saying something is plus something or something is minus something, I like to say I combine the numbers. Okay. So for example, if I have -6, right, and you'll see me use a lot of parentheses because the parentheses help me keep track of the signs, right? If I have -6 and I add it to a positive 3, right? A positive 3. I'll write that again. A positive 3, right? Essentially, what I'm saying is I'm combining the number -6 and I'm combining it with positive 3, okay? And that equals -3, okay? Or I could say that I want to combine -6 with -3 instead of positive 3, right? And then I get -9, right? So you see how when you use the word combining instead of saying plus or minus, you can keep track of the signs better and you don't get confused when you have like a double negative sign or something like that, okay? Because double positive sign is not such a big deal. It's when you have a double negative sign and then you have a plus and a negative together. That's when it starts getting a little confusing, especially when you have these really long problems that you're working. Or I could say I have a positive 6, right? and I want to combine that with a negative 3. Right? And that also gives me that gives me a 3, right? So notice that all 3 of these have a different answer, correct? Okay. So that brings us to this thing called scientific notation. And the reason why we use scientific notation in chemistry is because a lot of the chemistry that we do will involve numbers that are huge. They're either in the billions and billions and trillions of things, because that's the number of atoms there are in something, for example, or they're super, 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 super small, right? So we're talking like, you know, some number with a decimal and 23 zeros in front of it, right? So that's why we use scientific notation. It helps us make numbers more manageable because they get really big or really small, right? So for example, if I have a number like 2400, if I've got a number like 2400, I don't want to have to go through and write 2400 a gazillion times. I want to just use scientific notation. All I have to do is move the decimal point 1, 2, 3 spots, right? And then that gives me the number 2.4 times 10 to the third, right? 2 times 4 times 2 times 4, 2.4 times 10 to the third. And so 2400 written in scientific notation is 2.4 times 10 to the third, right? And what makes it even easier is that you can do it in your calculator easy too, right? So you could either go in and type in 2400, right, like this, and you'll get 2400, right? Or the equivalent thing would be to actually type in your calculator. Let's see if I can do it with you watching here. 2.4, right? Yeah, so you see there 2.4. But then, uh, and if you don't know that this is here, you can press the second key right there, and then there's the this calculator right above the x to the negative 1. There's this double E, and that double E stands for exponent. So now it looks like that, right? You see that? Oh, sorry, you see my face, but you don't see because it's see. So you see the E there, right? And that E stands for exponent. So that E right there actually represents that part right there, right? And all you have to do now is type in 3, right? So essentially on your calculator, what you have is 2.4 e to the 3, like that, right? And that means the same thing as this. These two things are the same, okay? Right? And then you can press equals, and that'll give you 2400. Okay? That'll give you 2400. Hard to see, but oh well. Okay? Um, somebody is raising their hand. Courtney. Courtney, go ahead and chat your question. Oh, there it is. Wait, no, chat your question or do it on the microphone.
Can you hear me?
Yes.
Okay. So can we use that 2.4e3 when we're writing answers, like in the lab, or do you only want us to use that e exponent when using a calculator?
So for me, it doesn't really matter. To me, it's the same thing. But again, I'm not the one grading your lab stuff, right? So I would imagine that in lab, Angie Dickens is going to want you to write times 10 in there. So
Okay, makes sense. Thank you.
yeah, no problem. Um, anyway, so yes, so that's how you do it real quick, right? So another way to do this too, right? So say we have the number, 0.0008, right? And we want to write that in scientific notation. It's kind of a pain to write out that many zeros, and it's hard to keep track of all those zeros. So again, this time instead of moving the decimal point to the left, right, to get to the number, I'm going to move the decimal point to the right 1, 2, 3, 4 spaces, right? And then so now I know then that this number is actually 8.0 times 10 to the, since it's a decimal number, it's going to be to the negative 4, okay? To the negative 4. And so, again, in your calculator, all you'd have to do is type in 8.0, right, e, and then negative 4. Sorry, that's a mistake. There we go, negative 4. and that would give you the exact same number. Now imagine how useful this is when you have something like Avogadro's number, which we'll talk about later, which is a number that has 23 digits, right? Or anything else that's in the billions or the trillions, right? Or trillions. And so that's because you'll find out soon that chemists are lazy, right? We like to take shortcuts. So all this stuff here is based on this thing we call the power of tens. Right? This is all based on the power of tens. Okay? So, for example, if I have the number 1,000, right? If I multiply that 1,000, if I multiply 10 times 10, right, 3 times, right, 3 times, that gives me basically 10 to the third, which is what? It's also known as 1 times 10 to the third, right? Which is also equal to 1,000. Okay? And I could go backwards with it too, right? Say I had 0.01, which is 1,000th with a th, and I can multiply 1 over 10, or 1/10, times 110 times 1/10 3 times, right? Which is essentially the same as saying 1/10 to the third, right? And that actually gives me 1 times 0 times 1.0 times 10 to the negative 3, which is equal to what? Also 0.001. Okay? So that's all based on the power of tens. Okay? You'll be doing some stuff later on in chemistry too called logarithms, which are also based on powers of 10. Like logarithms, right? And so if you look at your calculator, right, the logarithm button is right here, right? And that's based on the power of 10 right there. Sorry, you see my face, but you don't see the button. Right there is the log button, right? And then you also learn that to undo any logarithm, you can actually just do, you can actually just do 10 to whatever number you're trying to get rid of the log from, right? And we'll talk more about that later, right? We'll talk more about that later. But just be aware that right now, later on, you're going to start doing logarithms, right? But they're all based on the power of 10. There's also the natural log too. Don't get confused with natural log. Natural log is actually based on E, right? Which is 2.71 something, 7854 or something like that. You'll work on that stuff too, but again, the log stuff will be later. For now, just remember this stuff here, right? The scientific notation stuff. So, any questions so far about this simple math so far? I don't see anybody with their hand raised up, so. Okay, so, this is what I need. I need some Sudafed, right? Because not to make crystal meth, but for my runny nose and my stuffy nose that I've got going on right now. Okay, and the reason why I have this here is that this picture here is that one of the things that you'll have to do a lot in chemistry is figuring out what yield is, right? For example, you have a certain number of something, right? Or what percent of something is pure, right? Or what yield you have when you do an experiment, okay? So I'll give you an example here. This is a 12-hour Sudafed pill, right? This white one right here, right? Which I have like a whole bunch of them in my house because, not to make crystal meth again, just for my runny nose because it's crazy weather, right? And if you take that tablet right here, this tablet right here, which is what I have right here, right, and you weigh it, this is its weight, 0.7 grams, right? Which actually, we'll talk about it in more detail later, but that actually means it's 700 milligrams, right? It's 700 milligrams, okay? It doesn't say it on here on this box here because it says on the side. Oh, it does it actually. It does it right here. Sorry, right there. It says on the box though that this is a 120 milligram tablet, right? Or tablet. This is 120 milligram tablet of Sudafed though. So how come when I weigh it, it's actually 700 milligrams, right? So the question is then, how much of the tablet actually is Sudafed, what percentage of it is actually Sudafed, right? And what percentage of it is like all this other crap that they put in there, right? That doesn't even do anything. It's all filler, right? Just to make it look like you got more stuff there, right? So what percentage is actually Sudafed? Well, how would you figure that out? It's actually really simple, right? You have the number 120 milligrams right here, right? And you can put that at the top of a fraction. Okay. And then you get the total weight, which is 700 milligrams, and you put it at the bottom of a fraction, right? Now, if you didn't already know, the fraction line actually means dividing, right? A division line. And so what you're doing here is you're doing 120 divided by 700. And then you multiply that by 100 to get a percentage. And that gives you some kind of percentage, right? So if you look at the calculator here, right? And I don't know if you can see it very well, but it's cleared right now. I'm going to type in 120, right? I'll type in 120. Yeah, 120. And then I'll put in the divide button. And you see in there, this is why I like this calculator so much, because you can actually see the divide button, this divide sign. The other calculators don't actually show the divide sign. Okay. And then I'll put in 700, right? I'll put in 700, right? And then I can go enter, and that gives me 0.17 something, right? But then I've got to multiply it by pressing the multiplication button, right? I multiply that by 100. And so that gives me 17.14%. So only about 17.14 of the tablet that you're taking when you're taking a Sudafed is actually Sudafed, right? The rest of it is just fillers, binders, and stuff that makes it so that what they call extended release right here is actually true, right? It makes it so that it lasts the entire day, because this is a 12-hour Sudafed, right? And we can get through. If you ever take a biochemistry class or you take one of my drug classes in forensic sciences or something like that, we can talk about drug metabolism and why those fillers are important. But you think to yourself, you know, as a person just taking Sudafed, man, I'm paying Sudafed for Sudafed, but I'm only getting like 17% Sudafed in this pill. Why can't they just give me like more Sudafed, right? Maybe because they don't want you to make crystal meth with it. I don't know. You ever watch Breaking Bad, the show Breaking Bad? Walter White, that's what he does. He he uses Sudafed and he extracts it out of the binders, and then he makes crystal meth with it. It's crazy. Absolutely crazy. Okay, so any questions about how to do yield or how to do actual, actual mass or percent mass? Anybody? Questions? You're going to see that a lot. You'll see a lot where you have like some reported number and then some number that you got, and then you'll have to divide them and to multiply by 100 to get a percentage, right? You'll see that a lot in the lab. So keep that in mind. Keep that in mind. All right, so let's do a quick primer on how to solve equations, okay? How to solve equations, okay? So say that I have the equation. Oh, by the way, before we get into this, right, I cannot stress enough to you how important the order of operations is, except that it's not writing. Why is it not writing? Is my pen not working? Oh, it was not activated. Here we go. I cannot stress to you how important the order of operations is. Why in the heck is it not writing? It was working a second ago. Order of operations. And I don't know how you learned this as a kid in elementary school, right? But I learned it as, please excuse my dear Aunt Sally, right? And this is the order that you should do all mathematical operations. So the funny thing about it is, okay, so first of all, let's just go through each one. P stands for parentheses, right? E stands for exponents. M stands for multiplication. I think I put a little bit too many letters in multiplication there. That's okay. D stands for divide or division. A stands for addition. And the S stands for subtraction. Right? Now, yes. PEMDAS. Right, exactly. If you learned it as differently than I did, like if you learned it something else, a mnemonic different from mine, like my mnemonic was, please excuse my dear Aunt Sally. If you learned it some other way with other words in there to represent the initials of each of those steps, let me know in the chat. I'd like to hear everybody else's other mnemonics to remember this, okay? And so you have to do all mathematical operations in this order, right, to get the correct answer. So interestingly enough, the funny thing about it is that you can do things out of order, and sometimes you get the right answer, and sometimes you get the wrong answer, right? But if you use the order of operations, you will always get the correct answer, no matter what, right? And it's most important to use the order of operations correctly in a calculator, especially this one, because another reason why I really like this calculator is because it has parentheses in it, right? And since it has parentheses in it, it will go through and do everything you want in the correct order if you have them in the correct parentheses, right? If you just throw in numbers into this calculator without the parentheses, it will just do it in order of sequential. It will do it in order of sequence, like that you have it, right? Because the calculator is not smart enough to know what the order of operations is, right? But you are, so you need to tell it what to do with those parentheses, and that's why it's so important to use to do your math calculations and the order of operations, right? Very, very important. I don't see anybody putting in their mnemonics for the order of operations. Put in your mnemonics. What are they? Last year there was somebody that did something really funny, but I can't remember what it is now. So hopefully one of you guys did that. Put it in your chat. Come on, get in there. Don't forget that this is participation, right? Chatting is participation. All right, so we got here this equation: 2x plus 8 equals 14, right? My math teacher was a former Marine, so it was Papa Echo Mike Delta Alpha Sierra. I like that. That's good. I like that. Mode mass, brackets, off division, multiplication, addition, subtraction. I learned it the way you said it, of course. Aunt Sally. Yes, with Aunt Sally. What did I say? I thought I said that. Please excuse my dear Aunt Sally, Aunt Sally. I thought that's what I said. Oh, that's okay. All right, so good. All right, so if we have this equation here, 2x plus 8 equals 14, what do I do to solve for x, right? What do I do to solve for x? Well, the first thing I want to do is, when you're solving for x, what you're trying to do is you're getting x by itself, right? Get it by itself. Okay, you're trying to get it by itself. So the first thing to do here is the easiest thing to do, and the first thing to do here is actually to subtract. Oops, I don't know where I got 4 from. I apologize. You want to subtract 8 from both sides. So remember, when you're solving for an equation and you do something to one side, you've got to do it to the other side as well. Okay, you've got to do it to the other side as well. So that's why I subtracted 8 from both sides. And so what happens then is that the 8 that's on the left side of the equal sign turns into a 0. So now all I have is 2x, right? And the 2x equals whatever 14 minus 8 is, right? And that's 6. That's 6, right? So now what I do to solve for this x, right? Well, I'm still trying to get x by itself. And notice how to get rid of the 8 up here, I did the opposite, right? So the opposite of a positive 8 is what? A negative 8, and that's why I subtracted 8. Well, down here, right? Whoops. Didn't mean to do that. Sorry. Down here, we have a 2x. that means 2 is times x, right? 2 times x. And so I want to get the 2 away from the x, get the x by itself. If I have a multiplication of 2, what should I do to get rid of the 2? I should divide by 2, right? And if I'm dividing one side by 2, I've got to divide both sides by 2. Okay? So now 2 divided by 2 equals 1. So now it's just x, right? Because remember, if there's an x and there's no coefficient in front of it, then that number is a 1. Not a 0, but a 1, right? So now I've got x, okay? And then over here, 6 divided by 2 is what? It's 3, okay? So I literally just solved for x there, right? And x equals 3. Cool stuff, okay? So one of the equations or one of the formulas that we'll be flogging like a dead horse this semester is known as the ideal gas equation, right? The ideal gas equation. And the ideal gas equation is this: PV equals nRT. Okay, PV equals nRT, right? And P stands for pressure, V stands for volume, N stands for the number of moles, R is the ideal gas constant, and T stands for the pressure. Okay, and you'll get all kinds of questions that will ask you to solve for every single one of these variables, right? By giving you the other variables except for the one that you need, right? But that's easy because, you know, that's how you solve for. Pretend that one's the x, right? So for example, say I want to solve for V, or volume. Solve for volume, which is V. What do I need to do? Well, it's just the same thing as you did up here, right? Where you have a P multiplied by a V, and you have to get V by itself. So what do you need to do, right, to get V by itself? Well, up here, when you had a 2 multiplied by an x, to get rid of the 2, you have to divide by 2, right? Because it's the opposite of multiplying. It's the same thing here, right? So here, you divide by P on both sides, okay? Divide by P on both sides. And when you divide by P on both sides, you can actually cancel that out, right? Now it's 1V, but again, if there's no number, it's just a 1, right? So now you have V equals nRT divided by P, right? Does that make sense? I'm sure it does, okay? So now you can just plug in the number of moles, which is given, the ideal gas constant, the temperature, and the pressure, and then you can solve for the volume. And it's just regular mathematics there, right? Regular arithmetic. And here's where the order of operations is important. Because, excuse me, notice that M right here for multiplication comes before division, right? So what should you do first when you're solving for n equal nRT divided by P, right? It should not be doing the divide first, right? You should multiply the n times the r times the t first, and then divide it by P, okay? Because that's the order of operations. Like I said, sometimes you can do it out of order and you'll get it right. But sometimes you do it out of order and you'll get it wrong. But if you use the order of operations, you'll always get it right, okay? So always use the order of operations, okay? So let's try it with another variable, okay? So again, I have PV equals nRT, right? But this time I want to solve for the number of moles. We'll talk about moles later, I promise. But let's just say we want to solve for n, the number of moles, right? And so if I'm solving for n, what do I need to do now? What do I need to do now to get n by itself, right? Well, to get n by itself, I do the same thing I did over here, except instead of dividing by P to get V by itself, I'll divide both sides by RT, right? You can keep them together and divide them together, okay? By RT, right? And so if I divide both sides by RT, then the R's get canceled out, leaving behind a 1. The T's get canceled out, leaving behind a 1. And now my equation is PV equals PV divided by RT equals N. And now I have N by itself. And I can solve for N, right? I can solve for N. Good stuff, right? So that's how you solve for different variables in an equation, right? Different variables in an equation, right? So just to because we're going to be talking about this a lot later, right? Just so that everybody's clear, right? The PV equals nRT is the ideal gas law, right? I don't want anyone to get confused. Ideal gas law, right? And again, P is for pressure. And pressure is normally in the unit of ATM, okay? And then V is for volume, and that's usually in the unit of liters. And then we have, sorry, I have my dog is barking out there. One of my mini dogs, because I have 3 of them, right? Give me 1 second. I'm going to pause for just 1 second here. Sorry about that. I had to do with 2 things there. I had to blow my nose again, and then my dog tried to break into the study. So, oh, she does that. Good old Kiara. Anyway, so excuse me. So N again is a number of moles, right? And we'll talk about number of moles later. We'll talk about what moles are later, right? But moles are directly related to just for a quick thing, right? 6.02 times 10 to the 23rd, right? And that's either going to be atoms or molecules. Molecules. There we go. Molecules, right? And so that's what the number of moles are right there. And this is actually a constant known as Avogadro's number. Avogadro's number. We'll talk about that at length later on in life, I promise. And then the R here is actually the ideal gas constant, right? Oops, sorry. Ideal gas constant, and the ideal gas constant is is 0.0821, and it's got a very weird units. ATM times liters, mole times Kelvin, right? So this is known as Avogadro's number is a constant, right? That never changes. And then the ideal gas constant is obviously a constant that doesn't ever change, right? But then this last thing here we have is temperature. That's always going to be in Kelvin, right? The temperature, because we have Kelvin, we have Celsius, and Fahrenheit. Those are the 3 units of temperature, and we have Kelvin. So the ones I've boxed here, right, are the constants. They never change, right? Right. Sometimes you might be asked to solve for n, and it will be a different number, right? And sometimes you'll be given n, right? But if you're given the Avogadro's number is a constant. It will never change. And then, I wonder why it keeps doing that. And then the ideal gas constant will never change too, which is kind of like a lie because if you have different units, there's a different ideal gas constant number, but it's all the same number, just a different number because there's different units, which we'll get to in a second. But in here, the variables are actually volume, pressure, and temperature. And that's generally what you have to solve for, okay? So that takes us, now that we know the ins and outs of equations, right? The ins and outs of equations, okay? That takes us to graphing. Why do we need to know how to solve equations? Because we need to know how to do graphing. Graphing is a huge part of what we do in chemistry. And here we have a graph that shows on the x-axis temperature, right, and on the y-axis volume. Okay, and so you can see here we start out with 0 as the temperature, and it goes up to 100 degrees Celsius, right? And then here we start at 22 liters, and it goes up to 30 liters. Okay. And you can see as the temperature increases, the volume of the balloon increases, right? That line goes straight up. And so we refer to this as a direct relationship. So temperature and volume will have a direct relationship. Now, if the line were going the opposite direction, right, going backwards, then it would be an inverse relationship, right? But it's not, right? It's a direct relationship. As the temperature increases, the the volume also increases. Okay, and so um, we can use this kind of relationship to help us solve equations, right? And so solve some of our chemistry questions. Okay, so when you have a straight line like this, right, on a graph, it's actually something we call the y equals mx plus b, right, line of the equation, right, line of the equation, right? And so each one of these letters means something, of course, as always. Y here is the y value. Uh-oh, it stopped writing. There we go, y value. I don't know why it stopped writing. There we go, y value. And then x is the x value. And then b, right here, right, is something we call the y-intercept. Okay, y-intercept. So what is each of these? What is each of these, right? So the x value right here, right, is any number that's on the x-axis. The y value here is any number that's on the y-axis, right? Okay, so in this case, the x value will be a temperature always, and then the y value will be a volume always, okay? And then the y-intercept is where the y-axis is intercepted by the line, okay? Right? So this is, of course, like I said before, it's called the equation of a line. Okay, that's the equation of a line, right? So knowing that you have an equation of line, you can actually do a lot of things to solve for other things, right? So for example, we have this line here, right? And I want to be able to figure out what the volume of a balloon is at a certain temperature. I can use the equation of the line to do that, right? I can use the equation of the line to do that by plugging things in that I find on the graph, okay? So one of the things I didn't point out here yet is this right here, and that is the m. M is the slope, and the slope is probably the most important thing of a line, right? And it really is what a slope is the amount of x, right, and y right there, right? How much you go towards the x in the x direction, and how much you go up in the y direction. That's called the slope, right? And so every point on this graph right here has every point on this graph here has an x and y coordinate. Okay, every x has an x and y coordinate. Okay, and you can actually solve for you can actually look on the graph to figure out what each point's x and y is, right? So for example, right here, that point right there on the x-axis is 20. And then also here on the y-axis is 24, right? And so if you write it out in a coordinate system like this, you can say that the first point is at the x-coordinate of 20, and then the y-coordinate of 24. I'd say it's the first dot, but it's not really the first dot. It's like the third dot, that one right there, right? And my dog just broke into the room somehow. My dog just broke into the study. Okay, so there we have it right there, right? We have the x-coordinate and the y-coordinate at 20 and 24, okay? And then, I can go and look at another point maybe that's pretty cool, that's on a line that I can figure things out. For example, this one right here, there's a point right there, right? That's in the middle right there. So that's probably 70, right? And that one's on this line right here, which is 28, right? And so the x and y coordinates for this point right here, right, are 70 and 28. Okay? So you might be asking yourself, why am I even trying to figure out what these points are? Well, the reason why I'm doing that is because if I get 2 points on a line, I can actually solve for a slope, right? I can use these to solve for a slope. And if I can solve for a slope and I figure out what the slope is, I can plug that slope into the as for the m, right? And then I can figure out everything else from there. Okay. So, for example now, oh, so let me figure out the slope first. Let me solve for the slope first. Does anybody remember what the equation is for solving for slope? Well, it's m equals the change in y over the change in x, right? So remember I was telling you what the slope is over here. It's how much you move in x, right? And how much you move in y, right? So the change in x, right? And the change in y. And the equation is m equals, right? The change in y over the change in x. So this right here, the y, right? Divided by the x, right? This is the change in y and this is the change in x, okay? So I can expand that out if you remember from uh, uh, primary school, a lot of people actually call this the rise over the run, right? The rise over the run. Okay. And then that also then translates to this. This is how we actually figure out what the number is. It's always going to be the final or the y2 minus the y1 divided by the final x or the second x, right? Minus x1. Okay. And that will give you the slope. Okay. So all I have to do now then is to plug in these numbers right there, right? So we'll call these ones right here the x and y1, right? And then this is the x and y2, right? And so I can plug it in down here. M equals, right? What's y2? Y2 is 28, right? And then y1 is 24. All that is divided by x2, which is 70, minus x1, which is 20, right? And again, you know, I would actually put these in parentheses if you're in your calculator, right? Just to make sure that when you type in your calculator, it does the subtraction first, and then it does the, sorry about that, it does the subtraction first, and then it does the division because you need to do the things up here first. They're essentially parentheses above and below the division sign, right? I'll do that math real quick, and that actually ends up being 4 over 50. And then I can reduce that even further to be down to 2 over 25. And so now our slope is 2 over 25, right? It's 2 over 25, okay? Cool stuff, right? So now that I have the slope, this is the slope, 2 over 25, what can I do? I can now solve for the y-intercept using any 2 points on the any 2 x and y's on the graph, right? So again, I have the y equals mx plus b, right? And so let's say let me just use this group right here, this first set of numbers right there, in there, okay? So remember the y is literally the y, so what's the y value here? It's 24. And then our slope, which is 2 over 25, right? And then that's multiplied by our x, right? Which over here, our first set right there is 20. And then the plus, and then b, okay? And so now all you have to solve for b, and that's the y-intercept, right? That's great stuff because how do you solve? This is pretty easy, right? This is all by itself over here, okay? Already on the plus side, and you have these together, right? So what I would probably do then is I would go through and go ahead and subtract things over, right? So let's see here. Um, let's see how I would do this first here. Lost my train of thought here. Hold on one second. Yeah, that's what I thought I was gonna do. Okay, so I would literally all I would have to do here is subtract. I was thinking about maybe just multiplying these two out first and then moving them over, but I can just keep them together. So multiply. So I would subtract both of these over, right, on both sides. You could do that if you wanted to, just to make it easier to write out, I guess. Like multiply the 2 over 25 times 20 and then subtract it over, but you can just move them all together, right? So this one is subtracting from this one right here is subtracting from the right side of the equation, and this one is subtracting from the left side of the equation. So then I end up with 24 minus 2 over 25 in parentheses, right, times 20 equals B. Okay, and now you have B all by itself, and then you can plug it all into your calculator, right? And remember, when you're putting this into your calculator, you'll type out 24 first, right? And then put in the minus sign. So I'll do it for you real quick here so you see it. You type out 24 first, okay? And then you put out the minus sign like that, right? Can people see that? It's really hard to see, isn't it? I'm doing my best. And then you put in the parentheses, right? And I would put them in two sets of parentheses, right? Because that's two multiplications right there. 2 divided by 25. And I'll show you what I'm talking in just a second here. And then times, because remember when two parentheses are right next to each other, there's a multiplication, right? Times 20. Okay. I get B equals 22, oopsies, 22.4, right? And so now I have B, right? And what makes this so powerful is the fact that now that you have what B is, which is the y-intercept, and you have what the slope is, which is the where's that? There it is, the 2 over 25. You now know that your equation of the line is y equals 2 over 25, which is the slope, right, times x plus 22.4, right? And so the reason why this is so important and so easy and so awesome is that now you can plug in any value for y and then you'll get an x. Or you can plug in any value for x and then you get a y. So for example, earlier I was saying, I wonder what the volume of the gas, what the volume of the balloon would be if I heated the balloon up to 100 degrees Celsius, right? Well, I can't even tell from the graph because the line doesn't even go up that high, you know? The line doesn't even go up that high to 100 degrees, so I don't even know. Well, how would I know? Well, I could just take this 100 degrees and plug it over here, right? Plug it in right there for x, and that will give me a y. So I'll put in my calculator real quick. 2 divided by 25 times 100, right? And then all that plus 22.4, right? And don't forget to put in your parentheses. Sometimes you have to put it in after the fact, but that's okay. Sorry, I forgot to put in my parentheses. There we go. And then I get the answer is y equals 30.4. So notice that I can now figure out what the value is all the way up here, even though the line doesn't go all the way up there, just by having the slope and the y-intercept, right? Cool stuff. Cool stuff. Notice also too the y-intercept here, 22.4, looks a lot like where this dot is right here, right? Where that y-intercept dot is, right? Pretty cool. All right. We've only got a couple more minutes, like 15 minutes left. No, yeah, about 10 minutes left in the discussion, right? Any questions so far about how to solve for things? If not, I'll move on. Right. So why do we do all this stuff? Why do we go through and have to go do all this math and have to do all this graphing and solve for equations? And it's because we need to measure things in chemistry, right? So we already said this before when we are talking about the equations, but when you have volume, most commonly we use the metric system, which is the liter, right? Length, we use the meter. Mass, we'll use the gram. Temperature, we'll use Celsius or Kelvin, right? And seconds is time, right? So all these things are what we use to measure things in chemistry. And you'll have to know how to interconvert between them all, and which we'll do that in a different class, in the next discussion section. So these are what we called measured numbers, okay? These are called measured numbers. And so what are measured numbers? So if I'm looking at this ruler right here, right? And I'm measuring this piece of wood, it looks like it's at 4.5 centimeters, okay? But that's because I only have marks at every centimeter mark, okay? But if I were to get a ruler that had more marks inside, right? Turns out, if you look super close right there, right? It's not exactly at 4.5 centimeters, is it? It's actually at 4.55, kind of, sort of, right? That's more like 4.55 centimeters. A little bit more than 4.5 centimeters, right? So what that means is that a measured number is usually very uncertain, right? You're not exactly absolutely sure whether or not your measured number is correct or not, right? How close it is to the true value, okay? And that's called uncertainty. And the way we in chemistry decide how uncertain something is, right, is by using significant figures. The more significant figures you get, the more certain you are, the more precise you are, right? The more precise you are as far as the measurement goes. So obviously, since this one has more tick marks in it, this ruler down here has more tick marks in it, it's going to have more significant figures, right, than the one that doesn't have the tick marks in between the centimeter lines, right? And so the more tick marks means more precision, which means more significant figures, right? Which is cool, okay? So there are rules for significant figures, and we have to learn these rules now, okay? And the very first rule here is that a number is significant if it is not a zero, okay? So any number that's not a zero is significant. So here we have 4.5 grams. How many significant figures does it have? 2. Whoopsies. It's got 2 significant figures, right? If we look at this number here, 122.35, how many significant figures does that have? Put it in the chat right now. What do you guys think? Put it in the chat. Yes, you're right, Christopher. Anybody else in the chat? Good, good, good. Yes, yes. Everybody can see that that's 5 significant figures, right? Awesome, awesome. Okay, so that's definitely 5 significant figures. Okay, let's go to the next rule then. Okay, the next rule is that any zero between non-zero digits is significant. Right? So here we see 205 degrees Celsius, right? So that's got 3 significant figures because there is a 0 in between 2 non-zero digits. Okay? So for you guys out there, for the students among us, how many significant figures here? And 5.008. 4, yes, exactly. There's definitely 4. Good job. Good job. Okay, good, good, good. Everybody make sure you can see that there's 4 there, okay? Because it gets a little complicated in a second. The next one says a 0 at the end of a decimal number is also significant, right? A 0 at the end of a decimal number is also significant, right? And so here we have 50, just 50, right? So how significant is that, right? How many significant figures do we have there? It's 2, okay? I apologize there. There should have been there should have been a point there, a decimal number there. There we go. 2. There we go. Sorry about that. Must have been a typo. There should have been a decimal at the end of the thing, at the end of the 50. So then if we look at this one right here, 16 mils, how many sig figs there for the 16 mils, 16.00 mils? Anybody? Yes, no, 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 no. Someone put 2. That's not right. It's actually 4, right? It's going to be 4 because all the zeros at the end of a decimal number are significant. So you have to count these as well, right? So the answer there is 4. Okay? Answer there is 4. Okay? Everybody understand that? This is probably one of the ones that's a little bit more confusing. Is 0 at the end of a decimal number? So if it has a decimal point in it, right? And there's zeros after the decimal point in it, then those are definitely significant. Okay? I still see people saying 2. Why are people saying 2 for 16.00? I have someone with their hand up. Let me see. Let me take a gander at who. Bella, what's your question? Come on the thing and ask your question. Come on the microphone.
Hello, can you hear me?
Yes.
I wanted to know how is the 00 significant after the 16, after like the point, because like I don't get it.
Yeah, it's significant because you could just put no zeros there at all, and it would just be the 16. And what that would mean is, for example, you had a ruler that only went to that had 16 centimeters, but no other tick marks afterwards, right?
Yes.
But then if you had a different ruler that had 16 that had 16, right? But then it had tick marks afterwards to 2 points, right? To two decimal points.
Mm-hmm.
And that's why the zeros after a decimal point are significant, right? It indicates how precise the instrument is, right? How much smaller you can get in measuring it, right?
All right.
So that's why you have this here, where I had 4 centimeters up here on the, I had 4 centimeters on the ruler at the top right here, right? So that would have just been 4 right there. But this one down here, I can go to 4.55, right? Because there's more tick marks to get to. So it shows precision, right? Courtney actually says accuracy. Let's not confuse accuracy with precision. Precision is how small you can get something together, right? A bunch of numbers, how close they are together, right? But accuracy is how true the number is. So those are 2 different things. You can have a whole bunch of stuff, a whole bunch of numbers that are really close to each other, but they could be all the wrong value, right? Does that make sense? Bella, did you get that? I guess she did because she turned off her microphone. So, yeah, okay, there we go. All right, so that is one of the more confusing ones, but we'll have even more confusing soon. So this is great because scientific notation, right? The great thing about scientific notation, one of the other reasons why chemists like to use scientific notation, is that every number that is in the coefficient is significant. So you don't have to even worry about counting zeros, right? So for here, you have 4.8 times 10 to the 5, right? And that's how many significant figures? Well, the coefficient is the part that's in front of the exponent right here, right? So you're only counting the numbers in the 4.8. How many significant figures is that? That is 2. So in the chat, I want you to tell me how many significant figures are here in this coefficient for 5.70 times 10 to negative 3. How many significant figures do you see in here? Put it in the chat. Yes, good job. 3, yes. Exactly. All right, good job, right? So that's why chemists like to have things in scientific notation, because it's so much easier, right? And then the last thing we'll talk about today is when zeros are not, let's just do the second to last thing that we're going to talk about here is when zeros are not significant, right? So zeros that are at the beginning of a decimal number, right? At the beginning of a decimal number, they're not significant, right? So when you look at this here, which is 0.0000, sorry, I lost count, 0.0004 seconds, right? actually only has one significant figure because all the numbers, all these zeros ahead of it are not significant. Okay? All the zeros ahead of it are not significant. Okay? So that's a 1. How many significant figures do we have here? Put it in the chat for 0.075. 2. Yes, that is correct. That is correct. And then the last one is used as a placeholder in a larger number. So example, we have here 850,000, right? All the numbers after that are not significant, okay? They're not significant. Remember though, if they have a decimal point, then then they would be significant, but they don't, right? This one doesn't have the decimal point. So how many sig figs there? Just for the 8 and the 5 is 2, right? So for everybody else out there, what is 1.25 million? How many significant figures do we have in that one? Oh, I forgot to write up here. You're right. You're right about that one. There's 2. 3, exactly. Yes, we have 3 in this one. Good job. All right. So the last thing we're going to talk about today is since we talked about measured numbers, we have to talk about now exact numbers, which are so much easier than than everything else when it comes to significant figures, right? So what are exact numbers? Exact numbers are literally things that have an exact value. For example, if you have 8 donuts, you have 8 donuts, right? Or 2 baseballs, or 5 capsules, or maybe even like a dozen eggs equals 12 eggs. Those are all exact numbers, okay? And the reason why they're exact is because they have an exact number of something. For example, there are 365 days in a year. That's an exact number. No need for sig figs with exact numbers. That's why they're easier to use. And the reason why we have to know about exact numbers is because of the conversions, right? The measurement conversions. For example, 1 liter equals 1,000 milliliters, or 1 meter equals 100 centimeters, or 1 kilogram equals 1,000 grams, right? Or 1 foot equals 12 inches. 1 quart equals 4 cups, and then 1 pound equals 16 ounces, right? All those are exact numbers. So the thing to remember about exact numbers, which is the thing I want to leave you with today, right, is they are not measured, okay? You do not have to use significant figures in them, right? And they do not affect the number of significant figures in the calculation.